Well, hello, students of linear algebra. Welcome back to another video. So today's video is going to be about how to find the standard matrix of a linear transformation. In particular, suppose we're given a linear transformation, say T, which is mapping vectors in Rn over to vectors in Rm. We're going to want to find a matrix A such that T of x is going to be equal to A times x for any vector x in Rn, meaning that if you take that vector x in Rn and you see where it's mapped to under T, well, that should be just the same thing as multiplying x by a. And so the reason why we might want to do this is it's very useful computationally. There's a lot of applications to knowing the matrix of a linear transformation just for various reasons. And so what we're going to do today is we're going to go about finding a method to do that. And first we're going to actually kind of derive that method, showing you how to find the matrix of a linear transformation. The reason why I'm not just going to give you a cookie cutter 1, 2, 3, step 1, step 2 thing is there's no way you're going to just be able to remember that, or if you do, you're just going to be memorizing steps and you're not knowing what you're doing, right? And it's a lot easier, in my opinion, to memorize the steps if you know where the steps come from, right? And so it's not a very hard or long derivation. It takes a couple minutes. We'll just go through that, and then that's the general method for finding the matrix of linear transformation. You've seen where it comes from, and then we'll go through a few examples after that about how we can use this method to actually find the matrix of linear transformation, and a few different situations that you might encounter when you're trying to find the matrix of linear transformation. Okay, so first of all, with the derivation, there's a couple of things that we're going to need to recall. The first, obviously, is the definition of a linear transformation. After all, we are dealing with linear transformations here. And then the second is the standard basis for Rn and how we can use the standard basis to represent vectors in Rn. So starting with the latter, recall that the standard basis for Rn is going to be the n vectors e1 through en, where e1 has a 1 in its first position and then n minus 1 zeros below that. E2 has a 1 in its second position, n minus 1 zeros elsewhere, all the way through up to en, where there's a 1 in the very last position, the nth position, and n minus 1 zeros above it. And so these are the n standard basis vectors for Rn, which we can use to represent any vector in Rn. So given any vector x in Rn, say x is equal to x1 through xn, where this is a column vector, right? And these are numbers x1 through xn, which are just real numbers. We can write this vector x as a linear combination, remember, of the basis vectors e1 through en. In particular, we have that x is equal to x1 times e1 plus x2 times e2, summed up all the way through to xn times en, right? And so this is a linear combination of our basis vectors with the scalars that we use to represent x as a column vector. The second thing that we're going to need to recall in our derivation here is just the definition of a linear transformation. So let's write that down real quick right here. The first statement in the definition is that linear transformations distribute over vector addition, or in any words, for any vectors u and v in Rn, we have that t of u plus v is equal to t of u plus t of v, right? So you can add the vectors together in Rn first, then map them to Rm, or you can map them individually from Rn to Rm, and then add the resulting vectors. The second property of linear transformations is that they distribute over scalar multiplication. Or in other words, for any alpha, any scalar alpha in the real numbers, we have t of alpha times u is equal to alpha times t of u. These two properties together with the fact that we can write x like this is going to allow us to derive our general method for finding the matrix of a linear transformation. Okay, so now that we've recalled those two things, the standard basis vectors for Rn, as well as just the definition of a linear transformation, how can we go about finding the general method to be able to find a matrix A that lets us compute the image of any vector x under the linear transformation T simply by multiplying it by this matrix A? Well, first thing we're going to do is just take T of x, right? We're trying to find T of x, so let's start there. T of our vector x, and then remember that we've written x is nothing more than x1 times e1 plus x2 times e2 all the way up to plus xn times en. So we can do that thanks to our standard basis vectors. Oops. So that's the first step of the derivation. Second thing, we're going to go ahead and use this property here that linear transformations distribute over vector addition. In particular, this implies that if you have a third vector, say w, then you have t of u plus v plus w is equal to t of u plus t of v plus t of w, and so on and so forth. It extends to sums of any amount of vectors. You can prove that with induction, but don't worry about that. We'll just go ahead and use that. So what we can do is write this is equal to t of x1 e1 plus t of x2 e2 plus all the way up to t of x and en, right? Just using this first property here. And now we're going to go ahead and use the second property of linear transformations that they distribute over scalar multiplication. And now what we have is that our t of our vector x, remember this is just any given vector x in Rn, is going to be equal to x1 times t of e1, where e1 is the first standard basis vector, plus x2 times t of e2, plus all the way up to xn times t of en. So what this suggests then is that given any x in Rn, where x is just any vector in Rn, if we know t of e1 through t of en, then we can find t of x. So the linear transformation t, we only need to know these n vectors in Rm. Remember, these are going to be vectors in Rm because t is mapping Rn to Rm. But if we know what the standard basis vectors are mapped to by t, then we can determine t. And so this is the first step of the derivation, and from here we're going to use this to make our matrix A. Alright, so now that we've finished the first step of the derivation, and what we found is that given any vector x in Rn, where x is a column vector, say x is equal to x1 through xn, these are all just coefficients, the scalars in R, right? And then we have that t of x is equal to x1 times t of e1, summed up through to xn times t of en. And what we want now is we want to find our matrix A, right? So notice that this here, this sum looks kind of like a dot product or maybe a vector matrix multiplication, except for recall that also these are all vectors, right? These are t of e1, that's a vector in Rm, t of en, that's a vector in Rm. So we can write those all as column vectors if we wanted to. And also, with this being x1 through xn, it means that what we can do is we can write this whole equation here as a matrix vector multiplication of product, where this is the vector, this is just our vector x, right? This is our vector x in Rn, x1 through xn. And then this here, this is actually a matrix. It might not look like a matrix right away to you. You might say this is just a row vector, but no, remember that these are all vectors in Rm. So this has m entries, and there's n of them. So this is really an m by n matrix, right? And what we found is our matrix A here, right? We're done because this is t of x. And remember that that's just x, right? So if you want me to be more explicit about it, I can say that this matrix here is equal to A, right? And then this whole thing here, up here, is going to be equal to A x, right? This is x, this is A. So we found our matrix A, and that's how you find the standard matrix of a linear transformation. This is a general method that works for pretty much any linear transformation. All you really need to do is just figure out where your basis vectors from Rn are going. So it depends what n is. Let's say n is 2. Maybe you're mapping vectors out of R2. Then you just need to know where e1 and e2 go to. T of e1, t of e2. And then you just make a matrix that consists of those two vectors where e1 and e2 are mapped to. And that's going to be your matrix A. And so now that we've gone through this derivation, I have a few different examples that we're going to go through that illustrate how to actually use this method in practice, as well as different situations that you might encounter when trying to use this method. So let's launch into that. So now that we have our general method for finding the matrix of a linear transformation derive, we're going to get into some examples of how we can go about doing that in practice. So our first example, suppose that T mapping R2 to R3 is linear, and if T of 1, 0 is equal to -1, -3, 2, and T of 0, 1 is equal to 0, 0, 4, then what is the standard matrix of T? So this is fairly straightforward application in this case of our method, because we're literally given what the standard basis vectors of R2, in this case E1 and E2, are mapped to under our linear transformation T. And so given this information, we can form A directly from here. So in this case, our matrix A, we'll just call it A, is just going to be equal to -1, -3, 2, and then 0, 0, 4, right? And so this is a 3x2 matrix, right? And given any vector x in R2, so say x equals x1, x2, we could multiply x on the left by A, and that would give us our the image of x under the transformation T. Obviously, this particular example is fairly straightforward. We are literally given the exact information we need to determine the standard matrix just directly, and we are able to just write down the matrix given that information. So our next example will be a little bit more involved. Okay, so for our second example here, we're going to consider the map T mapping R3 to R2, and it's going to be defined by given a vector x, y, z in R3, it gets mapped to the vector x plus 3y minus z 2y in R2. Okay, and that is a linear transformation. We won't show that here, but what we want to do now is find the standard matrix for T. So in this case, we aren't actually given directly the images of the standard basis E1, E2, and E3 of R3. We're not given that. But what we can do, since we're given the formula that defines T, is we can just calculate them and then find the matrix. So it's going to be a two-step process this time rather than a one-step process. So the first thing we'll do is we'll go ahead and determine what E1, E2, and E3, the basis vectors for R3, what they're mapped to under this transformation T. Okay, so what we have is just literally applying the definition. We have T of E1, right? So remember that in this case we're talking about R3, so T of 1, 0, 0, and that's just going to get mapped in this case to just literally the vector 1, 0, right? T of E2 is T of 0, 1, 0, and that's going to get mapped to 3, 2, just using the definition of T. And then finally, T of E3 is nothing more than T of 0, 0, 1, 0, and that is going to give us just the vector -1, 0, and that is an equaling sign, so they're equal. And so now we've determined what the three basis vectors E1, E2, and E3 for R3, what they get mapped to under T. And so from here we can just write down the matrix that represents T. So in this case we're going to have that A is equal to 1, 0, 3, 2, and -1, 0. So in this case, now A is 2 by 3, unlike in the first example where A was 3 by 2, and that's because now we're mapping R3 to R2 rather than R2 to R3, right? So the dimensions of your matrix will reflect the dimensions of the vector spaces that you're mapping between. All right, now for our third and final example here, we have suppose that T mapping R2 to R2 is linear if T of 1, 2 equals 1, 1, and T of 0, 2 is equal to 2, 4, then what is the standard matrix for T? Now, this example is a little trickier than the first one we went through, because unlike the first one where we were literally just given what T of 1, 0 and T of 0, 1 were equal to, so we could directly use our method because we knew what the standard basis vectors for R2 were mapped to. Now we're given two vectors that, well, they aren't the standard basis vectors. However, because T is linear, we can still use these two images to determine the images of the standard basis vectors, and then use that to find our matrix A. So let's get into that. Okay, so the first thing that you might notice is that we have T of 0, 2, but we don't have T of 0, 1. But 0, 2 is only twice is just twice of 0, 1, right? That's all it is. So in particular, we have that 0, 2 is equal to 2 times 0, 1. And so what we're given is that 2, 4 is equal to t of 0, 2. But 2, 4 is nothing more than 2 times 1, 2, right? And t of 0, 2, well, that's t of 2 times 0, 1, right? And then using the fact that t is linear, we can bring that scalar 2 out and get that that is 2 times t of 0, 1. And so what we end up here is 2 times 1, 2 is 2 times t of 0, 1. 2 is non-zero, so we can cancel that from both sides. And what we found is, therefore, t of 0, 1 equals 1, 2. All right, and so in other words, 0, 2 is nothing more than twice of 0, 1, and so therefore t of 0, 1 is just half of what t of 0, 2 was, which in this case it was 2, 4. Half of 2, 4 is 1, 2. So that's the nice thing about linear transformations, right? We can use the information about one vector's image to find a different vector's image. So far we found that t of 0, 1 is equal to 1, 2, but we still need to find out what t of 1, 0 is equal to, right? The first basis vector. Now we don't have that, but we have t of 1, 2, and 1, 2, well, that's equal to 0, 2 plus 1, 0. So we're going to go ahead and use the other property of linear transformations here, that they distribute over vector addition, to find t of 1, 0 now. So what I'm suggesting is that since 1, 0 is equal to 1, 2 minus 0, 2, we know that t of 1, 0, therefore t of 1, 0 is going to be equal to t of 1, 2 minus 0, 2, which is then equal to t of 1, 2 minus t of 0, 2, because of the fact that linear transformations distribute over vector addition and subtraction, of course, too. And then we already know what these are, but we were given these, so 1, 1 minus 2, 4. And so that's going to be equal to negative 3, negative 1, negative 3. All right, and so now we have both t of 1, 0 and t of 0, 1. And so from here, we're ready to go ahead and apply our general method. Now that we know what the basis vectors are mapped to under this transformation t, we can conclude with the little space that we have left on this whiteboard that the standard matrix for t is going to be, so negative 1, negative 3, because that's where 0 or 1, 0 goes to. Second basis vector 0, 1 goes to 1, 2, and there we go. So in this case, RA is a 2 by 2 matrix because we're mapping R2 to R2. So once again, it reflects the dimensions of our vector spaces. All right, and that brings us to the end of this video of how to find the standard matrix of a linear transformation. And so just to summarize, we found a method here, which is that if E1 through En is our standard basis for Rn, where Rn is the domain of our given linear transformation T, then A is just the matrix consisting of the n column vectors, which are all length m, so they all have length m because they're in Rm, and there's n of them because there's a basis of n vectors for Rn. And the summary is just step 1, find those images, so find t of E1 through t of En, if not already given, right? Because like in the first example, we were just given that, so you might be able to skip step 1. Otherwise, if not given, generally you're going to need to either just apply the definition of the transformation t, or else use properties of the fact that t is linear. And then the second step is just going to be to let A equal t of E1 through En. You just form the matrix A once you have that information. All right, I hope this video has been helpful to everyone who watched it, and best of luck with your studies in linear algebra.